So now we know what interior points are in a set. These are the points that have a little bit of breathing room. Even if it's just a little bit, they can stretch their arms out, and everything that they touch within their little epsilon's reach is an element of their set. So the interior points are kind of the points that are surrounded by their friends from within the set. They're neighbors that populate the epsilon neighborhood around that point. So if everyone in one of my neighborhoods is from my set, then I'm an interior point. In this video, what we want to do is look at the other side of that equation. What if no one in my neighborhood is part of my set, except for myself? What if I am so lonely that there's some amount that I can reach my arms out such that everything that I touch is not part of my set, with the exception of myself? If I sort of stand alone in one of my epsilon neighborhoods as a point of the set in which I reside. We call those points isolated points, and sets which are made up entirely of isolated points are called discrete sets. Let's take a look at a good definition as well as some model examples for what discrete sets look like. So suppose that I have a subset of the real line. It kind of looks like this. I want to know, what would I look like if I were an element of this set that stands alone in one of my epsilon neighborhoods? What if I can have an epsilon neighborhood whose only neighbor from within the set is me, myself, and I? Well, I know what I wouldn't be. I wouldn't be one of these interior points. If I'm an interior point of the set, that means that I have an epsilon neighborhood, all of whose members, everyone inside my epsilon neighborhood, is an element from my set A. In that case, I'm an interior point. Now, I might have to have a very small value of epsilon in order to make that happen, but as soon as one such value of epsilon exists, such that everything that I can reach within an epsilon arm's length is an element of my set A, then I'm an interior point. And we don't want that this time. We want to look at the opposite of that. We want to look at the inverse. So what happens if I turn that on its head and say, under what conditions would none of my neighbors within an epsilon's length arm's reach be elements from my set A? What might that look like? Well, in the set that I've sort of sketched out here on the real number line, this singleton point that's kind of stuck here in between these interval pieces is kind of my candidate for what this might look like. So if I imagine standing here at this point and reaching out an epsilon's arm's length. Now, if my epsilon is too long, if I reach too far, I'm going to start reaching other elements of this set. But if I shorten my arms just enough, I will be able to stretch my arms out an epsilon's distance and not touch anything else from the set A, except for, of course, myself. And that's the situation in which we want to call that point an isolated point of the set A. It's sort of like where the isolated points are the ones with tons of friends surrounding them all the time from their set. The isolated points are like the hermits up on the top of the mountain, right? They belong to their own epsilon neighborhood, and they're the only person in that epsilon neighborhood, right? So those are the isolated points. Let's come up with a definition that's actually operationalizable within a proof in analysis or topology. So in order to say this accurately, what we're trying to do is ensure that the only element of the set A within my epsilon's arm's reach is me, myself. Right? Everything else that my arms can touch is not a part of A, but it's actually a part of the complement of A. It's outside of A. So to make that into a concrete definition, we'll say that X is an isolated point of the set A. If my arm span, so the epsilon neighborhood of radius epsilon around myself at X, so my arm span, and the set A, so all the members of the set in which I reside, so I do have to be a member of the set A in order to be an isolated point of A. But my arm span and the set A have something in common, so we'll use set theoretic intersection to join those two. So the intersection of the epsilon neighborhood and the set A, my arm span and the set A have in common only me, myself, and I. So the intersection of the epsilon neighborhood and the set A needs to be just the singleton set consisting of myself, just X. In other words, another way to read this is me, myself, and I, X, is the only thing that my epsilon neighborhood and the set A have in common. Now, how many epsilon does this need to work for? Well, again, even if this hermit stretches out their arms long enough, eventually they're going to be able to touch other points in A. So we don't need this thing to work for all values of epsilon, but if it works for even a single positive value of epsilon, then I must be an isolated point of this set. Another way that analysts sometimes say this is I am bounded away from the rest of the set A by a minimum distance of at least epsilon. Everything in A except for me is at least epsilon distance away from me. So I am out on an island by myself with respect to the rest of the set A. Let's look at some examples. If I have a set all of whose members are isolated points, so my set consists only of these isolated points, then we call that set a discrete set. So if all of its points are isolated, the set gets to be discrete. And a model example for a discrete set is the set of integers as a subset of the real numbers. What does a set of integers look like if we diagram it out on the real line? It just looks like a bunch of these points kind of disconnected from one another. In fact, all of the integers are separated from one another. They are bounded away from one another by a minimum distance of 1. Right? If I'm any of these integers, the next closest element in the set of integers to me is 1 unit away. And so there's no one within a shorter arm's reach. There's no integer within 1/2 of an integer. There's no integer within 1/4 of an integer. And so you can see how this definition of isolated point sort of falls directly out from that observation. If we pick any integer, if we pick it arbitrarily, any integer that we pick arbitrarily, the next closest integer to my right is going to be myself plus 1. The next closest integer to my left is going to be myself minus 1. And so if I'm standing here at x, can I find a value of epsilon such that there is no other integer within an epsilon's arm's reach of me? Right. How should I choose that epsilon? I just need to choose it so that I'm ensuring that I'm not going to accidentally reach to another integer from where I'm standing. So since the integers are separated by minimum distance of 1, as long as I'm reaching less than 1 unit of distance, I'll be okay. So as analysts often do, let's just cut that number in half to make it strictly smaller and decide that if my arms are a length of 1/2 and I stand at any integer, I am not going to be able to reach any other integer within my arm span. So if epsilon equals 1/2, then there exists such an epsilon such that the epsilon ball around my integer does not have anything in common with the integers other than the integer that we started from. So there's no other integer within arm's reach of any integer if my arms are only 1/2 of a unit long. So this is a prototypical example of what a discrete set looks like. But we could also ask the same question about some more interesting sets. So here's an example I want to conclude with. Suppose I have the set of all reciprocal non-negative powers of 2. Right? So 2 to the power 0, 2 to the power -1, 2 to the power -2, all of those, infinitely many. And then I'm also going to stick the number 0 into my set. Is this thing going to be a discrete set? Let's try to diagram out a picture, right? So the elements of my set consist of 1, which is 2 to the power 0, 1/2, 1/4, 1/8, 1/16, 1/32, ... And then I also stick in 0, just for good measure. So is this a discrete set? Are all of the points in this set isolated, bounded away from the other points of the set? Well, if I look at any of the members of this sort of sequence, the set of terms of this sequence, let's say I look at this number 1/4. Is that bounded away from the rest of the set? Well, sure. 1/4 is bounded away from its nearest neighbor by 1/8 minus 1/4 is actually equal to 1/8. Right? So probably if I'm going to write a proof that all of the members of the sequence are actually isolated points, maybe the arm's length that I could use to bound 2 to the minus n away from its nearest neighbor is I can't reach any further than 2 to the minus n plus 1. Right? So I can't reach from 1/4, I can't reach out any further than 1/8, or I'm going to be touching 1/8. So I'll probably cut that in half. Maybe I'll make it 2 to the minus n plus 2. Right? Then I know I'm reaching only halfway to my nearest neighbor, and therefore I know I'm not going to be touching any other elements of the set. So there seem to be a lot of isolated points in this set. But there's one that kind of sticks out from the others. What about 0? Is 0 an isolated point of this set? Well, let's take a closer look. So the question is, can I bound the point at 0 away from the other points that I included in my set? So if I were to plant myself at 0 and then reach my arms an epsilon distance out, could I ever get it so that I'm not touching any other element in this set? So if this is my epsilon arms reach, clearly I'm touching some other elements in this set. My epsilon's a little bit too big, so I'll try to shrink it a little bit. But then when I zoom in on this, I find out that I'm still touching a bunch of points. So I try to zoom in even further. But then when I zoom in further, I find out that I'm still touching a bunch of points. So I try to reach even shorter distance. I shorten my arms again. But if I zoom in, I'm still touching a whole bunch of elements in this set. So 0 is in fact not an isolated point, because no matter how hard I try, any epsilon reach that I have away from 0 is going to touch, in fact, not just one, but infinitely many elements of this set. So is this an isolated point? Not at all. In fact, it's an example of a point that we're going to see in our next set of videos called an accumulation point of this set. It's an accumulation point because any amount of distance that I reach out, I'm going to be able to touch an element of this set. So far from being isolated, there is no way for 0 to shake all of these neighbor points that are getting arbitrarily close to it. Now, why does that actually happen in this example? Well, if you've hung around real analysis long enough, you'll recognize that this sequence of points, if we think of it as a sequence, is a convergent sequence. It converges, and 0 is the limit of that sequence. And because 0 is the limit of this sequence of points, it means that for any epsilon that I pick, we can find a capital N, natural number, such that all of the nth terms in the sequence past that capital N are within an epsilon's distance of 0. In other words, no matter how short my arms are that I reach out, I will be able to touch, in fact, not just one, but infinitely many points. An entire tail of this sequence is going to be within my epsilon arm's reach, no matter how small I try to make my epsilon. So convergent sequences, even though the sequences themselves can be made up of just isolated points, and in fact, indeed in this example, 0 is the only point in this set which is not isolated. So even though this is not a discrete set, if I forget about including that 0, I do get a discrete set. But limits of sequences are sort of these prototypical examples of very often things that are not isolated points, because the terms of the sequence sort of accumulate on them, right? We can't shake them off. They get arbitrarily close to that limit by definition of convergence. And so that's where we're going to go next, is to think about what kinds of properties of sets can we look at by studying their accumulation points, the real numbers which the elements of that set sort of build up on and get arbitrarily close to and sort of crowd around, right? Those accumulation points are going to give us a way to look at the flip side of openness and get us a definition of what it means for a set to be a closed set. So that's where we're going next.